Hello, everyone, and welcome. We are going to wait for another 2 minutes or so for everyone to join and get started thereafter. Thank you. Dear supply chain practitioners and participants, welcome to this Sophus webinar. My name is Evrim Evinch. I lead the sales and marketing functions for Sophus in EMEA. We had a short-term change in plans. Joining me today is not my colleague Jonathan Nicholas, as shown here, who leads up our customer success function, but my colleague Byron Song, who will be presenting the demo to you today, who leads up our solutions function. Today, we will be showcasing how a demand forecast can be generated on the Sophus platform, which then seamlessly can be used to generate a supply forecast. We will begin with a quick introduction of our company, followed by an overview of the types of use cases that can be answered using the Sophus platform. Then we will introduce the topic of today, an end-to-end planning process from demand to supply, to segue into the demo immediately thereafter, and close the webinar with a summary. We are a young company founded about 5 years ago and have taken up the cause of making prescriptive end-to-end supply chain decision support affordable for everyone. We pride ourselves on providing the most advanced, complete, and easy-to-use supply chain decision support offering in the market. In those 5 years, we have won a good number of customers across the geographies of EMEA, North America, and Asia Pacific. You see some of those customer logos on this slide. Due to the nature of what we do, we can serve supply chains in any industry, although the use cases to which our technology is applied may vary by industry. In spite of being in the market for a short time, we have been recognized by Gartner as one of the leading technology providers for supply chain network design. This and the following slides summarize a number of ways our technology can be employed to answer supply chain questions. The color coding of the circles around the icons indicate whether these uses are strategic, tactical, or operational in their nature. You will notice that beyond typical supply chain network design concepts, our technology supports further analyses like carbon emissions, taxes and duties, risk and resiliency, and planning-related topics like inventory, CapEx planning, sourcing, and outsourcing decisions, supply network planning, cost to serve optimization, and more. There are two major value propositions our technology offers. Proposition 1. As shown on the previous slide and this one, our platform can be used to answer questions which do not fall into the category of supply chain planning in the narrower sense, but require answering nonetheless, such as the minimization of carbon emissions. Proposition 2 Supply chain questions should be answered such that objectives such as profit maximization, cost minimization, or service level maximization are achieved by balancing all factors against each other with an end-to-end supply chain view. This slide illustrates that holistic approach by showing various questions that require optimal answers and also require alignment with each other, depicted here in their logical sequence of dependency. This prescriptive alignment across all echelons of the supply chain is an approach that planning software struggled with, but provides superior results to the textbook planning process, where individual steps are conducted sequentially in a linear fashion. As our topic today is a planning process, I want to spend a minute to explain how the Sophus platform typically interacts with planning and other systems. If you've attended our previous webinar, you will have heard how we discussed the use of our technology to determine parameters that are used as input to planning systems, which are then used to create supply plans. We will be looking at a somewhat different approach today. Apart from also covering the demand forecasting process, on the supply side, we will be showing how the Sophus platform creates a supply forecast. In other words, we will not just be determining parameters for the further peruse in a planning system in our demo today, but we will actually be generating the forecast itself. If the Sophus platform is used in this fashion, there is no need to use an APS, an advanced planning system, anymore. However, to be precise, a true planning system would not only provide a supply forecast, but would actually go a step further and generate order proposals that would be fed back to the ERP system for execution. For simplicity purposes, we're not going to cover this step of the process today, but stop at the generation of the supply forecast. So now to talk about the first part of our demo, the demand forecasting process. It consists of the following steps. First, Sophus automatically obtains all of the data it requires to generate a forecast. These include the demand hierarchy, which can be flexibly defined, including the elements shown here. Further SKU-related master data. Potential regressors that are suspected to be influencing demand in certain industries called causal factors. The histories of our own demand and of the potential regressors being evaluated. And finally, the forecasts of these potential regressors that the system would use in generating our demand forecast. Thereafter, planners can make manual adjustments to some of these parameters, like specifics of new product introductions and end of lives, event types, and similar. They can also analyze which potential regressors the system identified as having a strong causal relationship with demand and choose to include or exclude the forecasts of select regressors for the augmentation of the demand forecast. Once these human adjustments are completed, Sophus will automatically cleanse outliers. If required, planners can adjust model settings before the platform generates the demand forecast automatically across all levels of the demand hierarchy. Once the forecast is generated, planners can make manual adjustments to it to arrive at an unconstrained consensus demand forecast. In that process, they are supported by various KPIs. And to complete the picture, once the supply plan has been generated, which is the second process we will demonstrate in the course of the webinar, a constrained consensus demand forecast becomes available, which may or may not be congruent with the unconstrained version, depending on how constrained the supply side is. Please do feel free to submit your questions through the Q&A function as we proceed. I will now hand over to Byron to actually go through the demand forecasting demo piece for you. Byron, you can take the screen if you like.
Thank you. Hopefully you can see my screen now.
Let me just check. Yes, we can.
Fantastic. Right, so I'm here logged on to the Sophus platform using a browser. I'm using Google Chrome. I created a folder called Forecast to Replenish Plan. In this folder, you can see there are two models. And I'm going to first demonstrate the first model. And this model called Demand Forecast The purpose of this model is to look at the last 52 weeks of demand and some of the business causal factors, and then try to predict what the next 8 weeks demand is going to be. And this result, which is the forecast of next 8 weeks, will function as the supply forecast to Everyone's point earlier on that slide. And this demand signal will feed our second model, which answers a different question. It's looking at the optimal plan to replenish our different DCs and supply different customers. But we'll come on to that later. First, let me go into this demand forecast model. For people who have used Sophus before, you would understand that we have a standard schema, a standard database which you can just populate different tables to build your own models. There's basic elements such as the periods. Like I said, we've got history of 52 weeks plus 8 weeks that we're trying to predict. So altogether, we got 60 weeks in this model. You can have tables for your products. You can define your customers and facilities. You can also put your historical demand in the customer orders table like this. So you can actually see by customer name, by product name, what the historical demand was by order date. And this history of a requirement will form the basis of the machine learning algorithm to try to extract trend, seasonality, other statistics to help predict what the future demand are likely to be. But in addition to the to the historical data of demand, we can also feed the algorithm with some further causal factors. And these causal factors can come in different formats. For example, these can be events, such as the holidays, such as the back to school season data. So you can define your own events in this table. You can name it whatever you want, and you just need to specify which customer group, which product this event apply to, and the date of this event, and the likely of effect of the demand on the demand. So you can either specify that's an increase, decrease, or set it to be automatic. So the machine learning algorithm will detect the relationship itself. So that's the type of event we can put in here. You can also define sales price by customer, by product, by effective date, and the value of the price to help the algorithm to see if the historical and future price will likely affect our demand. Further, we have these regressors. So this table, again, is a very customizable table. You can use this to capture any factors you think are likely to affect your own demand. And you don't need to really screen through many different factors here. Just anything you feel could be positively or negatively affect the demand, you can just put in here. And then leave the hard work to the algorithm to work out which factor actually matters. And you can put not only the history of the sales target or whatever causal factor that is. We have a sales target here as example. You can put the history of your sales target as well as the future sales target. So the algorithm, if it thinks this is an important causal factor, it will try to predict the sales based on these future targets. Populating these inputs, again, to everyone's point, you don't have to manually type them in for sure. We have the ETL tool that can help connect to your other systems. Just to give a very quick example, you can use this type of workflows to connect to other databases and extract information and automatically populate your models and your tables. And you can even schedule these tasks to run at a regular cadence to keep your model always live. So that's the most of the inputs. We can also create alternative scenarios. And these scenarios are based on the single database that we just looked at earlier. Without copying that database, you can create a scenario item to switch elements on and off or change certain values to form an alternative scenario. The advantage of this is the ease of managing multiple scenarios without creating many models, but also the ability to compare the results of these scenarios side by side very easily and see what has changed. Now, in this model, we have a baseline, which is just what the data was in the input tables, but we also created 2 additional scenarios just to test different things. The first scenario is we would switch on the sales target causal factor to test if that has a important effect on the forecast accuracy. And the second scenario is we're gonna switch on the iteration plan. The iteration plan is basically the product substitution. If you have a new product in the same category that's going to replace the old product, you can capture the plan here. For example, I've got this 14-inch laptop 1 being the original product name, and the new product is called laptop 2, and this is the substitute product name. And I can specify by which date the percentage of the product that's going to be substituted. So with this, you can tell the algorithm to not only predict the future demand of this category, but also specify which product that demand should be attributed to. So after we set up these scenarios, we can just run the algorithm of any of these scenarios. You can just select all and click run. We already run them, so I'm not going to do that again. But I'm just going to show you the output now. So first, you can look at the output in a tabular format. We've got summary table. We also got the detailed forecast value table. And just to show you this most detailed table, I can filter the result by scenario. For example, I can look at the baseline. I can look at a certain customer, and I can look at certain product. And then we can see by period, which is our 60 weeks. We got 60 records here. We have the historical value, which is input, but we also have a forecast value based on the machine learning forecast. And also we can see from week 53 onwards, these are forecast period. So we no longer have actual values, but the algorithm will be giving us the prediction of what that demand is likely to be in the future. If you want to visualize this in a more intuitive way, we can build these dashboards. And let me just talk you through the results using this dashboard. So I have selected a particular product. I can change to any other product or all of them. And I can select the 3 scenarios that we've run. And here in these line charts, I can see what the actual value was versus the forecast value. And again, we can see that the last 8 weeks, we don't have actual value, we just have the forecast value. And just by looking at the 2 lines, we can already see that the results are pretty close. If I scroll down, here I've built some more intelligence on the weighting factor of the different causal factors. So we have different type of factors like the statistics, the events, and calendar. So from this, we can see the prediction of this product future demand, the biggest factor type is statistics, which is the historical demand. But if we just focus on the events itself, we can see the Christmas and back to school seasons are most important factor. As we can see here, the back to school season is over the summer. Maybe the students are getting ready for their start of the term. So there's a peak of the sales of laptops. And also during Christmas, we have a uptick of demand as well. For a simple single measure of the forecast error, we are using weighted root mean squared scaled error. So this value basically gives you a simple indication of how good the results are. And the smaller the value, the better. And 0.56 is pretty good. And down here, we also listed the different event factors that was considered by the algorithm, and I'm ranking them by the importance. It's basically the similar information as the pie chart. Now, if you want to compare multiple scenarios, I built another dashboard that allows us to choose which scenario we want to look at, and then it compares the baseline on the left versus the selected scenario on the right. And this way, you can easily tell what is changed and whether including the causal factor is increasing the accuracy. In fact, we can see here, comparing with the baseline, when we increase the sales target, is actually reduced slightly, ever so slightly reduced accuracy. So it's not a very good indication of demand, the sales targets. And also, if we want to look at the iteration plan taking effect, we can also compare the laptop 1 and the laptop 2 in this scenario 2. So when we switch on the iteration plan, remember we seen earlier that laptop 2 is the new product that's going to substitute laptop 1. So in this scenario, we can see laptop 1 demand forecast has really dropped down to 0 gradually in the next 8 weeks, whereas laptop 2 is taking over the total demand between this category. So the end result, as we've seen earlier, is a forecast of the next 8 weeks demand, which is the intelligence that we didn't have before running this algorithm. We've seen how we can test different causal factors using scenarios, and we can also introduce product substitution if we want to. But the end result is we have a particular scenario that we want, and we have the demand signal ready to be processed further. So that's the end of the demo of the first model. I'm going to hand it over back to Avram to set the scene for the second part of the demo.
Thank you, Byron. Can you confirm that you're seeing my screen, please? I'm assuming I'm presenting.
Yes, you are.
Okay, thank you. So now moving to the second part of the demonstration today, which is the supply side. We have just generated an unconstrained consensus demand forecast that Byron has shown to us, which is augmented with a determination and application of causal factors that improve the forecast accuracy. Now, the logical next step is to see if and how this demand could be met on time and full at the highest level of profit or least cost and maximum service level. In our example, the forecast generated will be sitting on 15 demand points, which are served through a 2-echelon supply chain network with 15 distribution points and 2 plants. Plans do not ship directly to the customers the way this model has been built. And thanks to the flexibility of our platform, we could have easily modeled a supply chain that is more complex, for example, with multiple supplier echelons and additional nodes in each echelon. Once the optimized results are available, the primary outputs we get from this model are the supply forecast from the plants to the DCs and the constraint demand forecast. We also get a raw material forecast. However, because we have not included suppliers in this model, we're not told from where the raw materials should be sourced. Therefore, I put this one in brackets. Additionally, the supply plan provides us with further details, such as an inventory projection and the allocation of product flows through the network. Those details could be more numerous, but are not in the demo that Byron's going to share in a minute, if we had decided to build the model accordingly. Some examples for such further details that could be generated are illustrated here in faded color. And as we also want to showcase how easy scenario analyses are in Sophus, which as Byron has already alluded to earlier, we'll also take you through examples where we will analyze the effects of further parameters applied across 4 different scenarios, which will be building upon each other. Byron, you can take the screen again and continue with the demo, please.
Yes, thank you. Right, can you confirm you can see my screen?
Yes, we can.
Fantastic. Right, so the second part of the model, as everyone said, is the supply model. And this model has a complete network footprint. So you got manufacturing sites, DCs, and customers. And you can add different type of supply details to it. You can have work centers, you can have resources, you can model the different production processes and bill of materials, etc. But the key point is this model will take the output of the first model, which is the demand of next 8 weeks, and derive a best supply flow considering the various constraints, such as which site and work center can produce which product, what's the maximum capacity of these nodes, and also the inventory constraints, such as the minimum, maximum days of stock of cover, and then give us the holistically optimum plan to do so. So let me go into this model now and explain a couple of elements of this model. So first, have a quick look at the size table. So in addition to the customers, we have in this model the DCs and the MFGs, manufacturing facilities, which we didn't have in the previous model. We also have a customer orders, and this is actually the same information as in the previous model, the forecast part. So we can see the 8 weeks that had been forecasted from model 1 by customer and by product. We have a table called initial inventory, and this table will give us the definition of on-hand inventory, as well as the in-transit inventory and work-in-progress inventory. So the aim for this is to set the input for the planning of the next 8 weeks. We not only need to consider what we already have on hand, whether that's a finished product or raw material or intermediate material. We also need to know that there are certain products that's being made or being transported to our site, and they will arrive in a certain time during the next 8 weeks. So we can define by site, by product, a date in the horizon when this in-transit inventory will become available. In addition to that, we can also define some constraints in the model. For example, we have here by DC. So here I can see by this in this DC Boston, we have a maximum and a minimum inventory constraint. And when you create a constraint, this can be done in different unit measures. You can define number of units or kilograms or cubic meters, or even the value and price of the total inventory. But in this case, we are using days of stock as a way to dynamically constrain the inventory position as the most healthy inventory level. So we don't want it to be too high or too low. Ideally, it will be between 20 and 25 days of stock. So this is kind of defining the upper bound and lower bound of a corridor of inventory position we would ideally be in. Now, within Sophus, we can define this constraint as a hard constraint or a soft constraint. So in this case, we know it's possible that the inventory constraint is not feasible. For example, when the demand is too high, you may have to dive deeper into your safety stock and go below 20 days of stock. We don't want the model to be infeasible and not giving us a result. Rather, we want the model to try to stay within that limit and tell us when it couldn't do it. So the way to do that is simply switch that constraint to a soft constraint by setting this value to true, and then give it a penalty cost. So that's a unique feature of Sophus to consider this constraint as a soft constraint and also consider this penalty cost in the holistic optimization. Another thing I would like to show you is the inventory policy. So in the inventory policy, we can define by site, by product, what the inventory holding cost is. So over here, I have defined the handling cost, inbound, outbound handling cost, but I also have defined some storage cost. So this is an incentive for the model to reduce inventory wherever possible. But obviously, if the minimum threshold of 20 days is activated, that will kick in and will force the model to keep at least 20 days of stock, even though it will trigger some inventory holding cost. And just finally, I want to talk to you about two pieces of constraints that we will be testing later on in scenarios. The first one is about flow constraints. So in this model, we have two transportation modes. We have less than a truckload and full truckload. And in each of these two modes, we want to test a conditional minimum flow constraint. So that's telling the model if you use full truckload, for example, on the lane, you have to ship at least 50 cubic meters, which is a conditional minimum constraint type. If you don't have enough volume, you'd have to wait to the next week or the week after until you have enough to send a shipment. This clearly will change the frequency of shipment and quantity of replenishment and create more of a sawtooth activity on your inventory level. So we will be testing this constraint and see how the sawtooth chart look like and how we can best to consolidate our shipment to not only satisfy this type of constraints, but also try to stay within the inventory corridor. This is one type of constraint that will generate this kind of restriction on replenishment. Another one I want to talk to is this production policy. In the production policy, we can see which site can make what product So like this, we can see this product is being made at that site. And over to the right, we have a field that we can use to restrict the minimum production quantity. Now, when this is populated, any value that's above 0, the model won't be allowed to make any less than that value in that period. Similar to that conditional minimum flow constraint, this will cause the sawtooth chart to be higher. So we may have to wait till we accumulate enough volume to buy from this supplier, or we just ship a large replenishment order and keep it in the DC to consume for longer. But either way, that is affecting our replenishment and inventory holding behavior. So having gone through those inputs, I'll just quickly talk you through the different scenarios that I've set up. The baseline is just running the optimization as it is without any inventory constraints or any conditional minimum or production constraints. And then we start to overlay the model with some days of stock inventory constraint consideration. So that's the inventory corridor activated. And then after that, we added on top of scenario 1, the consideration of full truck load conditional minimum. So that's the 50 cubic meter minimum shipment size. And then on top of that, we also added minimal production quantity for one of the laptops to be 1,500. So we're not making anything less than that in every week. And finally, I have a scenario where we try to limit the total production of a product. And that could be, for example, factory maintenance or shutdowns. So we just have a disruption of the production capacity, so we can't fulfill all of the demand. But in that scenario, I will allow some of the orders to be lost or delayed, and we can look at the service level, what service level impact based on these production capacity constraints. Again, we can use the dashboard to give us a very visual understanding of what's happening. So if we just look at the baseline to start with, we can see we got some inventory targets, 20 and 25 days of stock. We can select any size and any products. And the orange line represents the inventory position in the next 8 weeks. When there's no inventory, like I said, the model is going to try to reduce inventory to 0 if possible. Then we don't see that week at all. But now, if we go to scenario 1, where we activate the days of stock requirement, then we can see there's inventory in all of the weeks, and the model is reflecting the replenishment and the consumption of inventory from week to week. And there are going to be weeks where we are a little bit lower or sometimes higher than the minimum and the maximum threshold. But the model is going to give us a plan so that we are back to the normal desirable inventory level as soon as possible. So this is after the model has tried all the possible combinations and gave us a best plan that will deliver this inventory position graph. And if you want to understand what actually is the plan for production and for replenishment, we've got tables here to show exactly that. So here we can see by scenario. So if we look at scenario 1 and look at by this site, we can see the different production timing and quantity of each laptop. And this is already optimized result. Similarly, you can also extract your optimum replenishment plan by scenario, by source and destination. And you can see from this Columbus factory to Austin, DC. We're replenishing in week 1 and week 4 only. We're skipping 2, 3, and 5, 6, 7. If we want to compare different results, different scenarios, again, we can use the different dashboard. Here, I've got scenario A and scenario B. You can always choose your own scenarios to compare. So here I'm comparing scenario 1 with scenario 2. So the difference is scenario 2 has added constraints on the conditional minimum shipment for the FTL mode. And as expected, we can see the sawtooth chart became a bit higher, but the model does bring us back to the desirable inventory level as soon as possible, as much as possible. And we can compare the production plan, replenish plan of the two scenarios, and there's no sales loss in either scenarios. And fast forward, when you compare scenario 2 with scenario 3, again, a bit higher production quantity results in higher inventory level as well. But that's expected behavior. And if you compare scenario 3 with scenario 4, apart from the fact, so we're looking at this laptop 3, which means we have limited the inventory, the production capacity of laptop 3, if you remember the setting of the scenarios. So what happens is we will reduce our inventory to 20 days, and we will not fulfill demand anymore. And we can see that the model has shown the loss of sales in this scenario. The behavior obviously is subject to the input value of the data we're using, which is dummy data. So you can make it so the loss of sales is more expensive than protection of your inventory, for example, and then you see a different behavior. But this demo is really trying to show you what could happen based on this input data. What's the business levers you can test in these scenarios, and how you can generate a demand signal in Sophus and use that demand signal to help you plan your production and your replenishment activities in the near horizon. That's all I wanted to say about the demo. I'm going to hand it back to Avram to show the closing slides.
Thank you, Byron. If you could please confirm again that you can see my slides.
Yes, we can.
Thank you. So wrapping this webinar up, I would like to highlight some of the various good reasons to choose to work with us. Starting from the top right, we provide the leading supply chain modeling and optimization technology in the market. Built on a real cloud architecture, our platform is able to solve the more complex supply chain problems at significantly faster speeds than the established competition. Further, as data handling is a critical requirement for successfully utilizing this type of technology, our platform provides built-in capabilities to exchange, validate, and manipulate data automatically. Moving down, we're able to operate at the pulse of the market as we're not part of a larger organization or have commitments to provide short-term returns on venture capital investments. Moving to the bottom left, we know that providing best-in-class technology is necessary, but not sufficient for our customers to reap the maximum benefit from using our software. We therefore ensure that we closely align onboarding and development plans with our clients and support them with various services during their use of the Sophus platform. Finally, in the top left, we advocate that optimization technology provides superior results in planning processes than established advanced planning systems. through the prescriptive results it generates, its flexibility of incorporating further decision criteria without the need for customization, and through its simplicity in generating what-if scenario analyses, our platform is better value for planners' money. This reflects itself also in the numbers. Our customers typically obtain a 3-digit return on their investment into the Sophus platform and get their investment paid back through an improvement of their bottom line within months. In the rightmost box, you can see the typical savings intervals for several supply chain cost types we see our customers pocketing. If there are no further questions, let me just double check if there are any questions submitted. Now would be the time. Otherwise, we would be wrapping up this webinar, so let's give it a minute. I'm assuming no questions are coming, so thank you very much for attending. We will be wrapping up now. Thank you.